We have Sandeep Shiyekar, sir, highly accomplished structural engineer and civil engineering professor with over 30 plus years of experience, a PhD doctorate from IIT Mumbai. He has completed postdoctoral research at Virginia Tech under NASA grant, contributing to the projects with NASA and Airbus. Sandeep Shiyekar, sir, welcome to our today's session. I hope you
Hello,
are
good evening.
listening to
Good
me.
evening to all.
Good evening, sir. His expertise includes advanced materials, composite laminates, and structural dynamics. He has led 200 plus design projects and secured research funding. And he has published extensively, files to IPRs, and guided multiple PhD and PG students.
Prospective candidates for the GATE examinations. So the first part, today's first part was covered by Dr. Indrajit Jain. He covered the rigid body mechanics, wherein the displacements are, we are not calculating the displacements in the rigid body mechanics. And what is meant by rigid body means the distance between any 2 points will remain unchanged before, after, and during the application of the load. So this is the concept of rigid body, and the same concept is applied in the applied mechanics. The second part is presented by Dr. Pradeep Tapkir sir. He presented the strength of material. So this is also called the mechanics of deformable bodies. So in this mechanics, we are dealing with the structures with the deformations. And the deformations may be the displacement, linear displacement, and the angular displacement. So the first of all, going further for the structural analysis, that the flowchart that we need to understand very well. The flowchart is what? First is the displacements, then the strains will be there, then the stresses will be there, and the stresses will leads to the forces. So ultimately the displacement and the forces are interconnected, or vice versa also. The force will also create the displacement. The force, stresses, strain, and the displacement. The reverse order and the either order can be possible for the structural analysis. So in the structural analysis, the displacements, these are called the kinematics. The kinematics are very, very important. To understand of the structure means understanding of the structure, how the structure is going to behave. So basically the structural analysis that what we are dealing here is the discrete structure, is the skeleton structure, wherein what is meant by the skeleton structure means the sectional dimensions are very, very less than the length. The length of the member is much more than the B and D, that is the sectional dimension. These structures are called the skeleton structure or discrete structure. Other structures, these are called the continuum structure. The continuum structure may be there as a plate structure or shell structure. That we are not dealing with the plates and shell structure. We are dealing only with the skeleton structure. And the skeleton structures are basically the first structure, the skeleton structure, that the two-dimensional truss. The two-dimensional truss is the first, what you can say, the skeleton structure. Then it will be the two-dimensional frame. Then it will be two-dimensional grid will be there. Then three-dimensional truss will be there, and three-dimensional frame will be there. So this is the, what we can say, the skeleton, the various types of the structures that what we are dealing with. Now, before this structural analysis, what we learn in the engineering mechanics is that the structure can be solved by using equilibrium equations. What are the equilibrium equations? That these are the three equilibrium equations that we know, that summation fx, fy, and m is equal to 0. But that is not the true. This is applicable only for the two-dimensional structures. But for the three-dimensional structure, that summation fx0, fy0, fz0, mx, my, mz0. And these are equilibrium equations are derived from Newton's second law of motion, that F is equal to ma, correct? As there is no acceleration, so acceleration again it is derived from the displacement. Then it comes to the velocity. Then if we differentiate the velocity with time, then we will get the acceleration. So if there is no displacement in the structure, then the acceleration in any direction x, y, z must be equal to 0. So the side part is 0. So that's why we have got the equilibrium equation. That is nothing but the Newton's second law of motion. And the structure, basically there are two types of structure. One is statically determinate structure and statically indeterminate structure. So statically determinate structure means what? The structure we can solve. The structure we can solve by using the equilibrium equations. These are called statically determinate structure. And what we cannot solve, these are called the statically indeterminate structure. What is meant by the analysis? What is meant by the solving of the structure? See, the structure is uh, subjected to the various loads. So don't mix the load and the forces. See, the loads are dead load, live load, wind load, earthquake load, snow load. These are called as the loads. These are not the forces. And these are acting on the structures, right? And because of the loads acting external loads, so the structure is going to resist this load into the form of the internal forces. Yes, the internal forces are the members of the structure. So the structure again, it comprises of the members and the nodes. So various members are connected by the nodes or the joints, what we can say. Nodes or the joints, these are the connection points between the two members, correct? Two or maybe the three members in the three-dimensional structure. So what I was telling that key, because of the external loads, so there are the internal forces that these are the resisting forces, and because of the internal forces equals to the external forces, and then it becomes the equilibrium in the structure. And the forces means what? This analysis means to calculate these internal forces means the analysis, correct? So what are the forces occur in the structural member? So structure means, so forces in the structure means forces in the members of the structure. So one member is there. Suppose we categorically classified the structure into beam and the column. First, if we could see the frame structure, then horizontal members are frame structure and vertical members are, horizontal members are beam and the vertical members are the column members. So, so if you consider a beam, then there are the shear force there, then the bending moment there, then the axial force may be there. But in the truss, there will be the axial force. In the grid, there will be two bending moments and one shear force, right? In the three-dimensional frame, there are all forces, means one axial force, two shear forces, then one bending moment, two bending moments, and one is the torsional moment. So there will be the maximum six forces in the member of the beam member of the structures. So depending upon the nature of the structure, we also classify the structure into two parts, right? That we have seen, that determinate structure and indeterminate structure, that we will see. So this is the syllabus, statically determinate indeterminate structure, that we will see. So in the structural analysis, the DS and DK, these are the two fellows are very, very important. DS means degree of static indeterminacy and DK means degree of kinematic indeterminacy. How DS we can calculate? DS can be calculated as number of unknowns minus number of equilibrium equations. Correct. So the if you see the truss part, if you see the truss, then how many forces there in the one member? How many forces? So tension and compression are the nature of forces, but it is an axial force. Only one force is there in the truss. So the NM means how many number of forces per member. So that in the truss, we can say it's a 1, right? 1 into M means total number of members in the truss. So how many members are there? That members will be counted as unknown forces in the truss, correct? And plus if you add R means total number of support reaction. Support reactions are considered as R. So in this type of the structure that is shown in the figure, so how many members there? There are 13 members. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13 members are there. So 13 members mean 13 into 1. 1 means what? This is the only axial force exists in the truss. So whether you go for the 2D truss or the 3D truss, the only one force is there, that is axial force. And the nature, the types of axial forces are tensile force and the compressive force. But the type is only the axial force in the one member. So 1 into 13, the 13 unknowns will be there that we need to calculate. So so one point at one joint, at one point there is a hinge, and at one second. And at 8 point, there is a roller. So how many reactions? 2 plus 1. So 3 reactions will be there. So 13 plus 3. So 16 number of unknowns. This is just for the example. 16 number of unknowns are there in this particular type of a truss. So how we can solve this 16? 16 unknowns. So we have learned the two methods in the analysis of the truss. One is called method of joint and the method of section. So if you consider method of joint, then how many equilibrium equations we are applying at the joint? So there will be two equilibrium equations that we are applying at the joint. These are summation fx0 and summation fy0. That in the assumption of the 2D truss analysis that we are not considering any kind of the bending moment in the truss or any kind of shear force in the truss. Only the axial force we are going to consider. So bending moment summation m is not applicable, and other forces are not applicable. So total number of equilibrium equations at the joint will be 2. Summation fx0 and summation fy0. So how many joints there? So there are 8 number of joints, right? So 8 into 2, there will be the 16. And total number of unknowns are also 16. So ds is, in this case, is 0. And what do you understand by 0? Means it is a statically determinate structure. Means this structure can be solved by using equilibrium equation. This is as simple as it. ds is 0. And when the ds is more than 0, means what? Either members are more or either the support reactions are more. These are called a redundant structure, or you can say it's an indeterminate structure when ds is more than 0. Either m is more or r is more than the equilibrium equations. So ds is more than 0 means it is a indeterminate type of a structure. Sometimes it also happens that the ds is less than 0. Means what? Either something is less, something is deficient. So this type of structures. So this philosophy is applicable to all. This is not only just I am telling applicable for the truss. This is just for the example how to calculate ds. So for the frame structure, that we will also discuss about the frame structure, how to calculate ds and all this thing. So this is just for the methodology to obtain the value of ds. ds means again number of unknowns and the number of equilibrium equations. Correct. Now ds is less than 0 means what? There is some members or there are some supports are less. Correct. That's why the ds value is 0. ds value is negative. Means what? It is called as a deficient type of a structure, or it is also called a unstable structure. Wherein ds is 0 and ds is more than 0, these are the, we can say, stable structure. But ds 0 means it is a determinate type of structure. ds more than 0 means it is a redundant structure, but it is a stable structure. Right. Now decay means what? What are the total kinematics in the structure? Means it's shown by the decay, degree of kinematic indeterminacy. So how the nodes are behaving, how the nodes are going to displace, that will indicate the value of decay. So how to calculate the decay? So decay can be calculated by number of joints minus multiplied by number of degrees of freedom. So in the particular type of a truss, every node is going in the is allowed to displace in the u direction, means the x direction, and also allowed to move in the y direction, that is the v. Means there are 2 degrees of freedom per node for the truss. So 2 multiplied by j. J means here how many j's are there? There are 8 j's, 8 number of joints. So 8 into 2, 16 will be there. But 16 we need to deduct the support reactions. So that will gives you the value of decay. The support reactions are 3. So 16 minus 3 will be equal to 13. So how the 13 will be there? If you see the node number 3, 5, 7, 2, 4, 6. will allow to displace in x direction, also allowed to displace in the y direction. There is no constraint for the joints 3, 5, 7 and 2, 4, 6. So how many there? 3 plus 3, 6. 6 into 2. 6 into 2, 12. And one more displacement is there, that is at the node of 8. 8 number node. If you see the node number 8, there is a roller support and which is allowed to move in the x direction. But it is not allowed to move in the y direction. But if you see the node number 1, this is not allowed in the x as well as not allowed in the y direction. But one more displacement is there, that is at the 8. So 12 plus 1 is equal to 13. So decay is 13 for this type of a truss. So this is the most simplest example that I have mentioned here. This is, you can apply this principle, this methodology for other type of structure. So to decide why the DS is required, to decide whether the structure is determinate, whether the structure is indeterminate. Also, it is also indicates that whether the structure is stable, whether the structure is unstable, or whether the structure is redundant structure. So DS is very important, and in gate examination, DS and DK are always asked by the gate. So you please and please concentrate more on the DS and DK, then I suggest you should go further for the further analysis. Okay. So this is all about the DS and DK. We will discuss further also. We will consider various types of structures, hinge, if internal hinges will be there, that we will discuss. But this is the basic philosophy for the DS and DK, to decide whether the structure is determinate structure or the structure is indeterminate structure. Okay, the word is there in the GATE syllabus, that is the method of superposition. Just I will explain what is the meaning of this method of superposition. So the deformations in the structure can be calculated by the linear addition of the deformation of individual loads. Correct? So if you consider this beam subjected to UDL also, subjected to point load also. So if I want to calculate the deformation, not only deformation, the support reactions also. If I want to calculate the support reaction or the displacement at any point, then I calculate the displacement by various methods. There are a number of methods by which we can calculate the displacement. The displacement by the UDL plus the displacement by the point load. That gives you the displacement for at a specific point by the method of superposition. Also, you can calculate the reaction at A, reaction at B by simply adding the reaction by the UDL and the reaction by the point load. This is as simple as it is. Just for the clarification, this is the method of superposition. Okay. So they have also mentioned the fourth method for the analysis of the structure. So in this structural analysis, my dear friend, we are dealing with the basically indeterminate structure. So determinate structure can be solved by the engineering mechanics, rigid body mechanics, applied mechanics. So in these examples, you will encounter with the indeterminate structures only. Correct? So you should not expect that the determinate structure will be there. Whether it is a truss, frame, beam, everything indeterminate structure will be there. So they have mentioned the force method. This is also called the flexibility method. This is also called the method of consistent deformation, right? This is as simple as it is. So this is the actual structure A. What is an actual structure? There is a point load at C. B is a prop. A is the fix. So this is simple prop cantilever with the overhang. Overhang is the BC. So how many reactions there? Just I will calculate the reaction. Reaction at A, reactive moment and the vertical force. I am neglecting the axial deformation in the beam. Summation effects will not be there. Axial deformation हम नहीं use कर रहे. So in the equation, so one equation will be less. So the reactive moment at A and the vertical reaction at A, there will be two reactions, one reaction at B. So total number of reactions are 3. And how many equilibrium equation we have? We have only 2 equilibrium equation. That is summation Fy0 and summation M0. So 3 minus 2, 1. So ds is 1. DS1 means what? It is a statically indeterminate structure. The first degree, very first structure, that is the prop cantilever. This is the prop cantilever is the first degree of statically indeterminate structure. Correct? So how to solve this? Because we need one equation now. So we are lagging one equation to solve this structure. How to get that one equation? So that one equation, we need to generate one equation by how? See. So first of all, we need to concentrate on the redundant. Redundant, that's we discuss about whether the redundant may be the member may be the redundant or the support reaction may be the redundant. So we consider, so we cannot cut the member. We consider redundant as either the support reaction at B. If we remove that redundant, then there will be two unknowns and two equations. The structure will be determinate structure. First part, first alternative. Second alternative will be if the moment, the reactive moment at A will be the next redundant. If I remove that, then there will be two support reaction A and B and two equilibrium equations will be there. So the structure is again determinate structure, right? So the first alternative we will work on. I'm going to remove the redundant B at B, right? So there will be the displacement delta BP. BP means what? The displacement at B because of the point load P. B, first B where? Where is the displacement B at B? And because of what? P. So the next letter will be P. Delta BP will be there, the displacement at B point. This is the primary structure. Now, I removed the RB. I removed the reaction. And for that, I have applied the RB is equal to 1. And because of, I will tell why 1, I will apply RB is equal to 1, right? So I will get the displacement delta BB. Means what? Delta BB means at displacement at B because of the load at B, unit load at B. Correct. Now, this is also called the flexibility method. What is meant by flexibility? Flexibility is a displacement. Again, it is a displacement produced by a unit force. It is a displacement produced by unit force, whereas stiffness means what? It is a force to produce the unit displacement. Correct. Now, delta BP plus, so this is small delta BB is the flexibility. Flexibility means what? It's a displacement produced by unit force. So if I multiply that flexibility by RB, I will get the displacement. And if I add both the displacement, delta BP and delta BB, then it must be 0 because B is the support. At B, there is a support, and that's why the new equation, new compatibility equation that we are going to get, that is delta BP plus RB into delta BB is equal to 0. And that new equation generated is useful to obtain the value of RB. Once we get the value of RB, then by using the equilibrium equation, you can also calculate the values for reactive moment and the RA. Next alternative is what? I remove the fixity. After removing the fixity, I will get only the hinge support because I have removed the fixity. There is only the hinge support will be there. Okay. Then just a second. Okay. Now, because of the load P, so displacement kinematics are both. Kinematics are linear displacement also. Kinematics are angular displacements also. So theta AP, again the notation, if you note the notation, AP, A means what? At, where? And P means what? Because of the P. So delta theta AP will be the rotation at A. This is the primary structure because I removed the fixity in the beam. I removed the redundant. I removed the fixity. This is the primary structure. And if I apply the unit rotation as applied in the first alternative. If I apply the unit force there, XA is equal to force, unit moment applied 1, then I will get some say alpha AA. So alpha AA is the flexibility. Alpha AA is the flexibility. Means what? This is a angular displacement produced by unit moment. So alpha AA is the flexibility. If I multiply, because there is a MA is there. So MA into alpha AA gives us the rotation. Similarly, the theta AP plus that MA into alpha AA both gives the rotation. But in actual structure, because of the fixity, there is no slope, there is no rotation. And that's why both are, if I add both the values, gives the 0. So this is again one compatibility equation that we get. And with the help of this additional equation, we can solve the structure. So this is the concept of force method or method of consistent deformation, or it is also called the flexibility method, that we will discuss details when we start our regular lectures. Okay. Next will be the energy method. Energy method means what? The work done by the load is converted into the form of energy. Suppose if you see the axial loaded member is there of length AL and area A. Because of the F, there is a displacement delta is there. If I plot the F versus delta load displacement curve, then because of the maybe the linear elasticity, there is a linear curve is there. And what is the energy? Energy is area under the curve. So area under the curve is 1/2 P into delta will be the area under the curve. And delta, as we know, that PL divided by AE. Stress upon the stress is directly proportional to strain. The stress is equal to E into strain. And using that equation, we can obtain the value for delta. Correct. Delta is equal to PL by E. So we are going to substitute P is N instead of P, and we will get the equation of the energy, that N square L by 2AE. So this is the equation for axially loaded member. That is the expression for the energy expression for the axial loaded member. Similarly, the same thing happens for the bending moment. So using that geometry, d theta is equal to m by EI into dx, and u is equal to that 1/2 m into theta, the same as 1/2 p into delta, the same m theta plot. If we plot, then you will get the linear displacement curve, and because of that, you will get 1/2 m into theta. And dui, if I substitute, see, if I substitute the theta, so du is equal to 1/2 m into d theta will be there. So if I substitute d theta as m by ei into dx, so I will get m square dx by 2ei. So what is the energy expression throughout the length? 0 to L m square dx by 2ei. Just you keep it in mind, these are the energy expression for the bending moment. Similarly, you can also derive the energy expression for the torsion moment also. That is the next part. But that only for the conceptual part, for the axial force and the bending moment, the energy expression, how to derive the energy expression, that we have seen. And these are very, very important in calculation of the kinematics, in calculation of the force. The next part is the slope deflection method. This is the most simple method. This is not involve any kind of a energy expression there. So directly you can use this equation. MAB is equal to 2EI by L, 2 theta I plus 2 theta I plus theta B, 3 delta by L plus MFAB, that is the fixed end moment. Similarly, MBA, if there is a continuous beam is there, A and B are the two supports, then MBA is equal to 2EI by L, 2 theta B plus theta A plus 3 delta by L plus MFBA. So MFAB, MFBA are the fixed end moments at A and B respectively. Theta A, theta B are the slopes at A and B, and delta is the sinking of support, either A or either B. So that we will solve the examples using the slope deflection method. This is the most simple method to analyze any kind of a structure, indeterminate structure rather. So the next method they have specified is a moment distribution method. So moment distribution method basically evolved from Hardy-Cross method. It is you can say it is not a exact method. It is an kind of a approximate method. It is a trial and error method by which you can analyze the indeterminate structure. So again, the structure is there, actual structure is there with the loading. This is the deflected shape of the structure. And what we have done is that every joint that whether it is the simply supported or whether it is a no support joint, we are going to fix the joint. A is already fixed, C is fixed, D is fixed, but B is not a fixed joint. So we are going to clamp. Clamp means we are fixing the point B, correct? We are going to fix the point B. And because of that, there is a anti-clockwise reactive moment will be there for at the joint B. And to correct that, because this is the additional moment because of the fixity that we have enforced in the structure. So we have to apply the corrective moment exactly opposite to the bending moment at B, correct? And this corrective moment will be distributed to the members BA, BC, and BD. So this is the simple as philosophy for the moment distribution method. Again, if you see the next diagram, MO is the moment applied at the point O. The point O is the junction of OA, OB, OC, and OD. These are the four members. Correct. Now, if we come back to the again three-member joint, this this M corrective moment, how this corrective moment will be distributed, that is given in these equations. So first of all, we need to obtain the distribution factor for OA, distribution factor for OB, OC, and OD. For that, we need the stiffness of OA. For that, we need the stiffness of OB, OC, and OD. How to calculate the distribution factor? The distribution factor, individual distribution factor divided by the summation of all distribution factors. So that will gives you the distribution factor for OA, OB, OC, and OD. And our objective is to calculate MOA, MOB, MOC, MOD. How to calculate that? Just you multiply the MO. Just multiply MO by the distribution factors. You will get the values for MOA, OB, OB, OC, and OD. So this is the general philosophy for the moment distribution method. Correct? Next part is this in the influence line diagram. This is very interesting topic in the structural analysis. A unit load, suppose there is a unit load which is moving from A to B. So how the reactions at A and reactions at B are going to vary. This will show by the ID. Not only for the reaction, but for the shear force at a particular point C, just point C, or bending moment at point C. So this is shown by the ILD, influence line diagram. And later on, if there is a you can say there is a UDL is there, then you can multiply the area under that UDL, then you will get the shear force, then you will get the reaction at A, B, and A, B in the structure. The structure may be determinate structure or indeterminate structure. So influence line, these are also very important. The questions will be there for the influence line, particularly for the bridges. Particularly for the bridges, through type bridge or deck type bridge, both the types of bridges they have asked in the examination regarding the IITs. The next methods are stiffness method and the flexibility method. These are the two methods. These are all, okay. These are all derived from the slope deflection methods. Correct. Slope deflection method is the originating method for this stiffness and the flexibility method. What is stiffness? Again, I am telling. This stiffness is the force to produce unit displacement, and flexibility means it's a displacement produced by the unit force. So that is that. F is equal to K into delta. That K is the stiffness. See, okay. So, and delta is equal to K inverse of F. That K inverse will be called as a flexibility. For this, just for the example, there is a spring of the stiffness F. There are two nodes, 1 and 2. The forces applied at 1 is F1. Force is there at 2 is F2. Displacement at 1 is U1. Displacement at 2 is U2. Then F1 will be what? F is equal to K into delta. K is the stiffness. So resultant displacement, net displacement at 1 can be calculated by U1 minus U2. So K multiplied by U1 minus U2 is equal to K U1 minus K U2. Similarly, F2 can be calculated as stiffness multiplied by net displacement at 1, that is U2 minus U1. Correct. So that equation also written there. That equation F2 is equal to K into U2 minus U1. So first equation F1 K U1 minus K U2. F2 is equal to minus K U1 plus K U2. And we will arrange these two equations nicely in a compact form in the matrix form. So matrix form is a very, very compact form. So in first left part, F1 and F2. So K is a one constant. K minus K, because U1, U2 are positive U1, U2. So I will arrange K in such a way that U1, U2 will get alternate signs. So K, K, U1 and U2. In this equation, we know F1 and F2, and we are obtaining the values for U1 and U2. This is called the stiffness method. This is also called the displacement method. Why displacement method? Because we are obtaining the displacement first in this method, where in the flexibility method, we are obtaining the forces first. That's why it is called the flexibility method, force method, consistent deformation method. Whereas in stiffness method, we are calculating U1, U2. How to calculate U1, U2? Because we are knowing F1, F2. Just get inverse of K matrix multiplied by the F1, F2, you will get the displacement. And as I told you, after getting the displacement kinematics, you can easily come to the forces in the members. So that is the simple philosophy as it is. Okay. So that is the very vague, very broader part of this GATE syllabus. So it is not possible to discuss everything here, but we will definitely discuss each and every problem of the GATE questions when there will be the regular classes will be there. Just for the example, okay. So see, so they have asked the one question. The first diagram, the diagram is of a beam, A, B, C, D, E beam. A is a hinge, C is roller, B and D are the internal hinges, E is the vertical roller is provided there. So this is one kind of a structure. Each length is L. Second structure is a square two-dimensional truss. A is a hinge, D is a roller, B is also a roller. Third structure is also a two-dimensional truss. Again, A, B, C, D, E, F. Right. So structure one, beam with hinge support at A, roller at C, guided roller at E, internal hinges B and D. Pin jointed truss, hinge support at A, roller support at B and D. Structure 3, pin jointed truss with hinge support at A and roller at C. This is in the GATE 2023. So what they have asked, which of the following statement is or are true? Both two statements are maybe also true or false. Structure 1 is stable. Structure 2 is stable. Sorry, structure 1 is unstable. Structure 2 is unstable. Structure 3 is unstable. All three structures are stable. All three structures are stable. So what the answer? So just I want to tell you, if there are some internal hinges are there. So what is going to affect in DS? First, we need to calculate the DS. Such question is there when need to calculate the DS. When DS is say DS is less than 0, means it's a negative, then you can say it's a unstable structure. Correct? So B and D, internal hinges, we are getting one more added equation, that is summation M at B is equal to 0, summation M at D is equal to 0. So we have got two added equation in the structure. That equation may be there, will be there in the equation of ds minus. So ds will be reduced if there are some internal hinges, right? So we will calculate the ds, and based on the ds, negative, positive, you can comment whether the structure is stable or unstable structure. See the next second part, second structure. It's a square truss structure. What is there? D and B, both are roller. But here, I want to say is that don't rely on the equations. See the physics in the structure. The equation may give the wrong values, wrong results. But if you see the physics, what will happen? What will happen? If I apply the force at C towards left, what will happen? A will be act as a fulcrum and it will going to rotate. The structure is not a stable structure. Structure is an unstable structure. Are you getting this point? Or if I pull the point C towards right, then also the structure is going to revolve, rotate at the point A. And hence, such rotating structure are not stable structures. So second is unstable, sure. If you see the third part of the structure, and I will give you one hint that a triangular structure is the most stable structure. Triangular shape. If any structure is having square or rectangle, this will leads to the instability, 100%. So that's why we are making the structure into the triangular subspaces, sub figures. If you see ABED is a simple square structure, and definitely it will create the instability in the total structure. So 3 is the also unstable. You calculate the ds for the first structure. If ds negative, then let me know what are the correct statements. So such kind of questions will be there based on the ds, and you see the physics. I again telling you all, the physics is very important. The equation may give you the wrong results for the ds and dk. Okay. So the next question is from the gate 23. The frame is given, overhanging frame is given, and they have asked to calculate. See, the magnitude of the moment reaction at A is WL square by K, and you calculate the K value in integer. So all the values must be in WL, all these things. So in terms of WL, you will get the answer. So whatever the answer is there, whether it is 3, 4, 5, 6, the K can be obtained. So this particular question can be solved by either you can use the moment distribution method or either you can use the stiffness matrix method. Correct? Using this, both the methods, you please solve this example and calculate the value for the K. Correct? So such type of examples are there. We will discuss more in the more lectures as per our schedule, right? Okay. So I think this is all from my side.
Thank you so much, sir. Thank you, all mentors. Thank you for delivering an insightful and well-structured session today. Your expertise has really created and value to our learning. Thank you once again. I request participants, if you have any doubts or any questions to be asked,
Yeah.
please feel free to ask the questions. We have our experts to help you out with the answers. Any queries?
Yeah.
We also have our director, Hitesh Lauti, sir. Would you like to have any inputs
Yeah,
from your
please.
end?
Please, sir.
Thank you very much, sir. And all three sessions were really good sessions. And even at this age, at this stage of professional stage, I could enjoy those nicely. I really feel that the students would be benefited with this a lot. Thank you, everyone, sir. We'll just wind up today's session. Thank
Okay,
you.
okay.
Thank you, sir.
Thank you, sir.
Thank you once
Hitesh, sir.
again, everyone. Thank you all.
Thank you.
Jain sir,
Thank you.
Shiyekar sir, and Tapkire sir. The sessions were very wonderful. Thank you, sir. Thank you.
Thank you, sir. Thank you.